So I'm sorry not to be in presence for this workshop, and it's great to hear several talks of former students or simply colleagues of Anatoly Vershik. And actually, there are many more. So it's strange to believe that Anatoly Message died, because even now, not only some development of his results, but really many his ideas, mathematical and not mathematical, maybe are so among us somehow. But it's like this. So I made my PhD under supervision of Anatoly Moiseyevich, and in the 2 years of this PhD, I learned many things that even many years later, so still one of my main interest in mathematics. And I hesitate for this talk. One very important topic that Anatoly Moiseyevich introduced me to is Poisson boundaries. You heard in particular in the talk of Vadim this morning the work about Poisson boundaries, about entropy. And today I have chosen another topic, also very much due to Anatoly Moiseyevich, about Følner functions. And you have heard in the talk of Misha Gromov this morning some historical discussion about thoughts of Anatoly Moiseyevich about Følner functions, and I will say more on that. So we consider a group, a finitely generated group. I don't recall the definition of the word metric, but simply we consider the Kelly graph. So vertices are elements of the group, and there are edges if you multiply by a generator. And this notion appeared already actually in several talks, I think, today. And we want to understand how large is our group. And one notion is the growth function. It's simply the size of the balls, something what was mentioned today already, something appeared in the work of Schwarz, of Miller, but now we know much more. This is one function. But the other function is the Følner function. This is the way to measure how amenable the group is. So this is a notion for amenable groups about asymptotic inequalities, and which measures this quantity describing is the group very amenable or not. So in the talk of Misha Gromov, you heard about his discussion, maybe even in 60s or something, about Følner function. But the first written appearance of Følner function, I believe, is in this paper of Vershik in 1973. I show maybe already the slide. So this 73 paper was an appendix to a Russian translation of the book of Greenleaf about amenable groups, about invariant means on topological groups. And in this Russian translation, there was appendix written by Vershik that in particular says the following thing. So it says here, I circled it in green, right? He mentioned this group. He doesn't say yet the name Reef product. In later papers it will be mentioned. It's a Reef product. He considered the Reef product of Z with Z. Reef products also were somehow mentioned, I think, in the talk of Tatiana when she spoke about lamplighter groups, in the talk of Vadim also about lamplighter groups. Here, Vershik considers not exactly lamplighter, he considers infinite lamp groups. So he considers this extension of the sum of Z, index by Z, extension by Z, and he says the following thing. For natural generators in this group, there is, he means a very natural Følner set, the set which the boundary is smaller than its size. Of the size, he writes 1 over epsilon, and this fibers 1 over epsilon plus 1. So we can denote 1 over epsilon by n. So he points out, he writes there is this cube, so to say, n this of size n, and the size of this, so to say, cube, it's not really a cube, but of the size of the set is n to the n. And Vershik mentions then, it seems that the Følner, there was no name of Følner function, but what he means, he says this function, right? It seems it should be like this, that is n to the n, and thus is different from the growth function. At that moment, little was known. It was only some hint of what can happen. But this idea that there is this very natural invariant and that it is very different from the growth function had a lot of developments in the last decades, in the last years, and I want to tell you about some of them. So Følner function will later discussed in, for example, in the work of Kamenovich and Vershik, in the paper about random walks. He discussed some properties relation to random walks, to return probabilities, to transition probabilities. And first question I want to comment, so which goes back to this paper Vershik, what functions are the growth functions? What possible function, if you give me some function and you ask can we have a group with such Følner function? And here a very general result is obtained by Bruxelles and Zheng, and they've proved the following thing, that under some minor regularity assumption on the function, you give me the function which is quicker than exponential, and then it is a Følner function of some group. So, like returning to this paper of Vershik, he says z with z, Reef product with z, it seems that the Følner function is quicker, it seems it's n to the n. And now we know not only n to the n, actually almost any given function which is more quick than exponential is a Følner function, but many very fundamental questions remain open. So one question I mentioned on my site is the gap conjecture of Grigorchuk about isoperimetry. And it's asked the following. If you have some group which is not of polynomial growth, is it true that the Følner function is always greater than exponential? This question wasn't discussed in this paper of Anatoly Moisеевич. Maybe I'll show you again. So here, the first question was, can it be really quicker than exponential? Maybe it seems to be strange to ask smaller than exponential, but in 73, actually, we did not know even that the growth can be intermediate, not necessarily exponential. So many things, what I find interesting in this is appendix to Greenleaf, that many, even more basic things were not known. So after we know them, some question asked here really seems very natural, but somehow Vershik guessed, I think, many interesting direction even before understanding some fundamental things about growth of groups. So I return to the slide with the question. So the gap conjecture of Grigorchuk. Maybe some of you know even more famous gap conjecture of Grigorchuk about the growth. And it is a bit more difficult to formulate because for the growth function, maybe I write something here. I have some problems inserting here. So for the growth, the gap conjecture for growth, it says unless the growth is polynomial, the growth should be greater than x square root of n, or in a weak form, at least v of n greater than exp n to the alpha. And this is a very difficult, very famous conjecture, which we don't know the answer. We don't have answer either for the gap conjecture about the perimetry. But you see the gap, so for the growth, at least you need to know some context to understand why Grigorchuk asked it, why x n to the alpha, why x square root of n. One needs to understand why square root of n. But for the gap conjecture or for Følner function, it sounds even more natural. I will explain you in a moment that exponential, there are many examples where Følner function is exponential. So among known groups, really, the minimal possible function known is exponential. And this result of Bruxelles and Zheng says anything greater, well, under some condition, is realizable. And it's a complete mystery whether we have really this huge gap between polynomial growth for growth and for Følner functions and really.
It's known, so this kind of behavior is known as stretched exponent, and it appears very often in disordered systems.
You mean exp and to the alpha?
Yeah.
Certainly, but for the growth, why should be it stretched? It was already a mystery to see that the growth can be not exponential and not polynomial, right? Now there are these Grigorchuk groups, right? And now some generalization, many other generalization. Thank you for this comment. Yes, of course, stretch exponential growth cannot be in various contexts, but just speaking about growth, I mean, even until now, it's some mystery when it can happen for growth. So to have a good intuition, what kind of stretch exponent, or should it be really a stretch exponent, it needs some intuition. And we don't know a group of growth x square root of n. This was my comment, right? But for Følner function, really lamplighter groups that we already mentioned, and maybe I speak a little bit more in a moment, it could be exponential, and there is this very simple formulation: is it always greater than exponential? And we still don't know at all. So some other remark about groups of Brusselli-Genk. So they constructed this very intrinsic family with very rich possibilities for isoperimetry and for some other asymptotic invariants. And not only it's related to this question of Vershik, but actually their construction is very much related just to this example mentioned by Vershik about Reef products. In fact, their groups are quite tricky, but limits of Reef products. But first, I want to say something about usual Reef products. So maybe I move here. No, maybe it's too early. So I just wanted to mention the work of Cologne Salef Coste, and I forgot on which slide I put it. Yes, I just didn't finish explaining some basic things. There is inequality of Cologne Salef Coste, also mentioned in Misha's talk today, something very fundamental. The Følner function is at least as large as the growth function for any finitely generated group. Again, this inequality, you see, it is proved in 93. So Vershik, when he asked his question 20 years before that, he didn't know yet this inequality, but it seems he guessed, so it's not stated explicitly, but one can understand from his paper, maybe he was guessing it should be at least as growth, that is, at least as exponential, because at that time, all groups of not polynomial growth were known to have exponential growth. But his first question, can it be not exponential, was answered by P.T. Salef-Kost in late 90s. They considered a different Reef product. They considered a lamplighter Reef product of ZD with a finite group. And they used the relation between return probability and isoperimetry. So for return probability, the asymptotics in this group is very much related to the asymptotic in the Donsker-Baradan theorem for ZD, just on abelian group. And then they use the general inequality to observe that there is an estimate for lower bound for the Følner function of this group, which is actually later turned out not to be not optimal at all, but at least it already answered the question of Vershik. Yes, for some Reef products, the Følner function is not exponential. And now, here I mentioned my result I obtained at the very end of my PhD, actually, says whatever Reef product you take, there is this lower bound for the Følner function, which is more or less asymptotically optimal. So for all the groups that we know, for the Reef products, it gives an asymptotically optimal estimate. Though some questions remain open even for these very basic objects as Reef products, because usually speaking about groups, about the asymptotic invariants, we don't look on precise answers. Usually we want to be able to change the generating set, and then we are obliged to consider functions up to some equivalence relation. But for some groups equipped with natural generating set, like Reef products, it seems natural to ask maybe very, very precise answer what is the Følner function, and here the equation seems to be difficult, and I will comment about some only very little is known about some very particular examples, but I need to move further. Just now I want to discuss various ways to prove the isoperimetric inequality, to prove lower bound. So Følner function is like this. The upper bound is just existence of some Følner sets, of some sets with small boundary. Sometimes for very tricky groups, even this could be difficult. For some groups like Thomson group, for example, even the question whether the group is amenable or not could be an open question, right? But for many other groups, upper bound usually is some straightforward construction sometimes. And the main thing to evaluate the Følner function, as Vershik asked, is the lower bound, right? Some question, or I'm not sure, or just some noise. So this argument for Reef product had a lot of development. First, several years after my work, there was a paper of Gromov who reproved the inequality for Reef products, improved the constant in this inequality, and observed that actually the argument, his argument, works not only for Reef products, but for any group which has many commuting elements. And so and then this argument was later used by, in particular, by Salov, Costa, and Zheng, and for some solvable groups in my work with Tiani. And so there were several works where at that time this terminology was not used, but now I want to say the number of linearly independent elements inside the ball. And the statement is like this: if you have a group, if inside the ball you count just number for returning to Reef products to lamplighter groups, it's the number of lamps, right? You consider a ball radius, consider some big ball of radius r, and you want to have many elements here, some, I don't know, gi's, which commute. And so in the previous work, commute and generates some product. So gi's, we want that inside our group G, inside there is a subgroup, there is a product of the group generated by gi, the product inside, and we just count the number of gi's, and this number provides a lower bound for the Følner function. And this works really in many groups, but something I think that was not noticed before, and I want now to report on my work of this year, joint with Josh Frisch, which has a very elementary formulation, and it says it's not necessary to count really what I call now linearly independent, when inside really there is a product. For example, if there is a product of z to something, right? For Reef products, usually we have z to some function, if it's the product of something with z, or it could be z pz to some function, right? There are many groups with this property. There inside this product, if you look inside the abelian subgroup, it's just linearly independent elements. So if this z to something, you can tensor it by q. So these are some elements that are independent over q. If it's z over pz, z over 2z, like for usual lamplighter groups, you also consider them just over this field. There is this number of linear independent elements. Now, what we noticed recently, that there is another invariant, and I want to explain it. So we consider group G, and on one hand, one can consider this number of linear independent elements, which is, I denote here, maybe it's not a good idea to write the same time. Maybe I don't write. So there is this number, I denote Li of R. Li stands for linearly independent. In many works that I mentioned now, we have this linear independent element. But now we noticed one can consider the number of what we call cube independent elements. First of all, one can consider this number Ci of R it's the number of cube-independent elements which appeared already in some works about growth, in particular, not in particular, actually, in my work with Tiani, but I think I forgot to write the definition. This is the main thing I want to explain today. So, sorry, I really have, but now it works. So, we have several elements. Let's call them G1, G2, G3, and so on. All inside the ball of radius R in our group. And we say they are cube independent if the following holds. We take G1 to some power epsilon 1, which is plus minus 1. And then we multiply G2 to the power plus minus 1. And so on. Gk to the power, some power epsilon k, which is plus minus 1. And we want to say that all these elements are distinct. This is, so to say, this generalized cube, because there is 2 to the k elements, right? Something to the power of plus minus 1, another thing to the power plus minus 1. So a priori, there is 2 to the k elements. Some could be glued. But we ask, so that there are these elements that you really see this cube. And this is a useful notion even before we ask that GIs are commuting. In particular, in my work, so here I mentioned my work on, in blue here, just I mentioned that this number of these cube-independent elements appear in our work about Poisson boundaries and growth of Grigorchuk group that gave this evaluation of growth. So speaking about usual growth, not about Følner function, about usual growth, there was this old question, and now we know to this most well-known Grigorchuk group, the first Grigorchuk group, we know the growth is approximately xn to the alpha, where alpha is an algebraic number, or algebraic of degree 3, which is approximately 0, 7, 6, 7, and so on, a little bit greater than 3/4. And so something about cube-independent elements appear in growth. But returning to our main question today for Følner functions, if we say just cube-independent elements, they don't say us much about the behavior of the Følner function. So just remove this. So if you consider a group which contains a free semigroup, for example, inside this free semigroup, you see there is this exponential number of cube-independent elements. So the number of cube-independent elements, just like this, is huge. But the Følner function could be not that huge. But I need to go to the next slide. Yeah. Yes, this isoperimetric lemma on this slide. I say, if we consider the number of cube-independent elements which commute, so we consider these Gi, so they really form a cube, and all of them commute. Each Gi commutes with each other, Gj. Then we claim that the Følner function is at least as large as exponent of this function, function that counts these cube-independent commuting elements. As I said, so very important in this claim that the elements commute. So if you consider Lamplighter group or any other among your favorite solvable groups, such as you can consider polycyclic groups, or you can consider Baumslag solitaire group, or a solvable one, which is a more right name, is Higman group, right? So all of them have this subgroup, sub-semigroup of exponential growth, and then it's, but the Følner function is not greater than exp n. But what we observe now, if this very elementary notion, simply this cube of commuting elements, then it provides a lower bound, which turns out to be optimal in some situations. So just a remark here on this slide, this cube-independent elements is the same thing that Erdős called just the number. There is this problem of Erdős in case of Z. You consider the interval in Z, and you want to understand the size of the set with distinct subset sums. So just to mention that what we call cube independent is the same thing as this notion considered by Erdős. And even on that, this is still a difficult open problem of Erdős. What exactly this number? So it's approximately logarithm, but what is it really? Because the subsets like 1, 2, 4, they're cube independent, but they are not optimal. Really, the very optimal answer in Erdős problem is still an open question. But for us, for the moment, we don't care about very precise estimate. We want to know the asymptotics. At least for Z, for abelian groups, the asymptotic is very easy to see. But our observation that even for much more complicated group of exponential growth, it is this number which gives you a very good idea about as a parameter in Følner function. So I want to give this dimension. Let's consider the Følner function. Take the log, and take lim sub divided by n, and take lim sub. And let's say this is as a parametric dimension of a group. For some complicated group, I write lim sub because the limit doesn't necessarily exist. Maybe one can say dimension is really well defined and the limit exists, but in general one need to write lim sub. Here there are many families of group. There are piecewise automatic group. There are groups of Kasabov-Pak, which you can consider as generalized piecewise automatic groups. There are groups with prescribed Følner functions, some in the work of Gromov and later in the work of Brissell and Zheng. And there are many groups where the limit here does not exist. And sometimes there are some groups, some of them even not so complicated, some solvable groups where the limit exists, but it does not need to be an integer. So in particular, the group of Brissell and Zheng, and also solvable groups we were studying with Tian and Zheng. So you can have any x n to the alpha for any alpha as an answer, as a Følner function. So in general, it's not an integer. But now, what we are proving now with Josh, that if you consider step 2 solvable groups, in other words, a metabelian group, then the dimension is really well defined and it is an integer number. So it's stated in this theorem. So we have an upper and lower bound. So whatever step 2 solvable group you give me, there is an integer d, and the upper bound is x per some constant n to the d log n, and the lower bound that we are able to prove for the moment is n d minus epsilon n. And moreover, one can say actually this answer is given by these functions of cube-independent commuting elements. It is a rare situation that for a group, we have some asymptotic and invariant, and really not anything, but really something related to integer occur. But can mention, of course, the growth of groups. If the growth is polynomial, or at least after you know, so it's Gromer's theorem that the group is virtually nilpotent, but at least when you know it's virtually nilpotent, the growth is n to the d. D is an integer. But a priori, it's not obvious before you know that the group is nilpotent, it's not clear at all why this d in polynomial growth is an integer, why it's not, I don't know, square root of 7, why it's not pi or something. But for nilpotent groups, at least there are these integer numbers in the degree for their growth. And now here you see at least some observation that for metabelian group, that there are some integer that show up. So there is very natural integers, and we want to understand better. Actually, we will again taking this maybe ambitious analogy with growth and with polynomial growth. It's not only the growth is polynomial when d is an integer, right? But the growth functions are really asymptotically equivalent to n to the d. There are no error terms asymptotically. And here for metabelian groups, what we believe that actually, yes, it's question. So what is written here is question 01. We believe really the growth is x n to the d or n to the d. It's clear just for usual Reeve product, you can have already these two possibilities. So for Reeve products with finite groups, you are exactly x n to the d. But for Reeve products with z, for these very elementary examples, again, you can have then x per log n to the d. But what we conjecture now that we really have exactly these possibilities for any metabelian groups. So something can be shown in this direction. So if maybe I mentioned on the previous slide, just let me check. Yes, in the previous slide I mentioned, if the group is torsion by abelian, then it's exactly x n to the d. Under additional assumption that the expansion is split, it was proven several years ago by Giacoboni, but this assumption that the extension is split is not important, it could be removed. We understand now it's always like this, so torsion by abelian is an easier case, it's really x n to the d. But the main thing to understand the torsion-free case. Take a metabelian group which is torsion-free. Can we understand what happens exactly with the Følner function? And it turned out that this question is very much related to purely algebraic question. And this question I mentioned here as question 02. I have 40 minutes or 45. I have 2 minutes left, or how many minutes do I have left?
10.
10 minutes.
10 minutes? Very good.
20.
No, 20, sorry. No. Probably,
I started at 05, I think 05.
yes. 40.
Maybe 10 minutes, right? I think 10 minutes, right?
6 and 0,
6.
6 and 50.
50 until 50.
So, anyway, I'm happy to speak. I have many things to tell you, but at least I have a few minutes, I believe, to explain this algebraic question.
Well,
So,
you can leave 5 minutes for discussion.
yeah, okay, but for the moment, I just at least need to explain this algebraic question about polynomials. So a priori, you see, our question is geometric, and actually, I didn't explain in detail the relation to random walks, but Følner functions are very much related to random walks. So it's a question a priori. We need to know good the structure of our group, the geometry, and the probabilistic behavior of random walks. But in our work, which we used in this theorem, I mentioned on the previous slide this theorem that gives up to some epsilon at least this behavior that you really have x n to some integer. And in this work, what we realized that the equation is related to equation which can be formulated without saying anything about group. It's simply a equation about polynomials. What we really need to know that if we have some polynomial, take an irreducible polynomial with integer coefficients in several variables, p of x1 and so on, xd. And we assume that it's not a divisor of two distant monomials. We call this condition generalized cyclotomic. If we have a cyclotomic polynomial, it's not good for us, but we assume it's not the case. And what we really need to know, does it all exist this integer number capital N, such that whatever other polynomial u in the same number of variables you take, and this polynomial u has coefficients only 0, plus 1 or minus 1. And we want to know that if you consider u of x1 to the n, x2 to the n, xt to the n, which it is not divisible by p. So this 0 plus minus 1 condition about polynomials, it's related to this cube independence. So for the group, I don't explain you normal forms. So we have a general metabelian groups. Actually, the normal forms could be complicated and not we really know them. But somehow these conditions, so for cube independent, if we have some abelian cube independent, it means we take this sum. If each gi, we take this coefficient plus minus 1, like in the equation of Ershler. And here, so this is informally this link. And what we really want to know to understand this question 02, and it's easy to see that if we have only one variable, this property holds if and only if the polynomial is not cyclotomic. So here the answer is yes. It is. We were able to check it for some polynomials, and in particular, if you take a Baum's law group, which contains a Rief product as a subgroup, some associated polynomial does has this equation, which leads to evaluation of the Følner function for Baumschlag groups. But we strongly believe that it's true in general. And if true in general, then it will give our answer here in the about Følner function. As I said, I don't have time to explain today something about Poisson boundaries of random walks, also one of the favorite topics of Anatoly Moisеевич, and certainly one of my main subjects of research. This question 02, today I hint you how it's related to Følner function. Actually, it would answer also many other questions about random walks, in particular about triviality and triviality of Poisson boundary of linear groups. And for the moment, we are really puzzled by this question. Maybe I also mentioned, I didn't write, this question 02, we ask in our joint work with Josh Frisch and Mark Richnovsky, and around the same time, Doug Lind and Klaus Schmidt ask a question which is in the same spirit, actually even stronger. They use different terminology, but more or less the equation is really also asked this question. So their work is not related to groups. So just studying polynomials, they found they were studying this property, proved it for a huge class of polynomials, but not for all. And they just, by curiosity, understand they wanted to know this question about polynomial. But for us, we are first of all interested in a possible application. It will really will allow us to have this really, I don't know, not dichotomy, but really this very precise answer for all metabelian groups, what is happening, and we don't know. Maybe the very last question, returning back to the paper of Anatoly Moisеевич about Følner function in 73, something that can be traced already in this paper, and I think mentioned a bit more explicitly in the paper of Vadim with Anatoly Moisеевич several years later. So what about the size of Følner function? Not only maybe size, what are Følner sets? So for abelian groups, I had some not very beautiful picture here, what happens in Z2, right? So in discrete context, like, in Euclidean space, balls are optimal, or here one needs to say optimally, asymptotically optimal. So in some groups, balls are best Følner sets. If the growth is exponential, it's clear all balls can't be Følner sets, that's for sure. But for many groups, like lamplighter, like Baumschlag solid, like polycyclic, like groups with finite preferred rank, the behavior of the Følner function, the cardinality is the same as the cardinality of the ball. So Følner sets certainly not balls, but they have the same asymptotics. And the challenging question, but there is no conjecture at all for the moment, can one characterize groups where the Følner function is the same as the growth function? As I said, Anatoly Moisеевич hinted that it's very interesting, it could be larger, and indeed, in many situations, it's important to understand how large it is. But now, what about, let's say, more naive situation, where the Følner function is the same as growth? There is no conjecture so far. It seems very interesting to characterize these groups algebraically, but if it could be done, it would be a very far-reaching extension of polynomial growth theorem about polynomial growth. And so for the moment, it's far from what we can understand. Maybe I stop my talk here in order to leave some minutes if there are some questions.
Questions?
Is the answer to your question 02 known for small values of D?
Small value of what?
Of D. When D is like 3 or 4.
No, here the most important to understand for D equal to. I don't say I have a reduction to D equal to D. I don't know what D is the number of variables, right? So
Yes.
Yes, no, here we don't know at all, and Klaus with Doug don't know either in their work. So even if the answer, yes, if there are two variables we don't know, and we really absolutely looking to understand. So
Thank you.
if you have maybe some ideas how to solve it even for d equal to 2, this would be a very important progress for us that we don't know.
Fedor Petrov has a question from internet. His question is, what about d equal to 1?
D equal to 1, that's as I mentioned. If there is one variable, it's an easy lemma. So first, maybe I should just write one line. First, something very easy. If we are cyclotomic of several variables, so to say, generalized cyclotomic, something that divides the difference of two monomials. If you take, for example, x minus 1, I'll try to write. No, that's not right. Okay. If you take, for example, x minus 1 or any other cyclotomic polynomial, it's clear it doesn't help to raise x to some power, even slash. If you write x n minus 1 is divisible by x minus 1. You can never guarantee if that it does not happen, right? So we have to, in this equation, we absolutely have to assume that we are not cyclotomic. Now, if d equal to 1, very easy to see that in the other direction, it's if and only if. Because if we take something which is not cyclotomic, we can assume, for example, we look on the roots. Assume, for example, that we have a root of absolute value greater than 1. Raising it to some power, we get something of absolute value equal greater than 2. Then it's very important that our polynomial u has coefficients 0, plus, minus, and 1. If you take a sum, the coefficients are only plus minus 1 of some numbers that grow quicker than 2 to some power, right? The sum cannot be 0. So for d equal to 1, this very easy observation shows really the answer is yes, right? It's if and only if. But for d equal to 2 already we don't know, and we really want to know.
Other questions, please. Okay, if not, let's send Annie.